Hello there. Thanks for joining me on this journey into one of the strangest questions ever asked. Does the universe itself have a history? It sounds simple, almost obvious. Of course the universe has a past. Every culture on Earth has told some kind of creation story. Yet the moment we step into modern physics, this idea becomes far less trivial. For thousands of years, the cosmos was imagined as a fixed stage, upon which the drama of stars, planets, and people unfolded. The actors moved, the scenery remained still. But what if the stage itself shifted? What if the background, the vast fabric of space and time, was not a silent, rigid container, but something alive, dynamic, and evolving? To understand how revolutionary this question is, we must begin with a poet. Rainer Maria Rilke once wrote that we humans are the bees of the invisible. We gather the honey of the visible world, light from stars, patterns in nature clues hidden in the sky, and transform these fragments into understanding. Scientists, in a sense, are the most relentless of these bees. They chase the faintest glimmers of evidence, carrying them back to the hive of human knowledge, hoping to construct meaning from what cannot be touched or seen directly. Nowhere is this more true than in cosmology. A long time ago, long before telescopes powerful enough to pierce the deep sky, our ancestors imagined cosmogonies myths that explained how the universe came to be. These stories were poetic, metaphorical, full of gods, chaos eggs, serpents, and cosmic battles, yet none of them questioned the background space itself. Space was simply there, eternal, static, a timeless container. Fast forward to the rise of modern physics. Galileo insisted that matter across the universe is fundamentally the same. Newton extended this idea by showing that all objects follow universal gravitational laws. Apples, moons, comets, planets. Everything obeys the same mathematics. Newton's universe was elegant, powerful, and predictive, but it was also still. Gravity could move objects within space, but space itself played no role beyond being an infinite stage. The idea that the universe itself might change simply did not exist. This is why the early 20th century was so shocking. In 1915, as the world tore itself apart in war, Albert Einstein quietly introduced a new way of thinking. His general theory of relativity didn't just adjust Newton's equations, it rewrote the very meaning of gravity, space, and time. According to Einstein, gravity is not a force at all. It is the curvature of space-time, a geometric bending that guides planets in their orbits and shapes the trajectories of light. Suddenly, the universe was no longer a passive container. It became a physical entity with its own properties, capable of stretching, warping, and responding to matter. Yet even Einstein himself did not immediately recognize the full implications of his discovery. He imagined a universe that was graceful, eternal, and static, held in delicate balance. The equations of relativity, however, refused to cooperate. They suggested something outrageous, that space-time could not remain still. It had to change, either expanding or contracting. This was deeply unsettling. A dynamic universe felt too philosophical, too dramatic, almost mythological. Einstein resisted the idea and altered his equations to force the cosmos into a static state. Later, he would call this modification the greatest blunder of my life, though even that confession carries mythic exaggeration. What matters is the tension the universe Einstein wanted did not match the universe his mathematics described. Before we go further, imagine this simple scene one Einstein used to explain his insight. Picture a blind beetle crawling along a sheet of paper. The beetle believes the paper is flat because it cannot sense anything else. But if the sheet bends or curves, the beetle continues walking without realizing the ground beneath it has changed shape. In Einstein's analogy, we are the beetle. The universe is the sheet. We live inside space-time, unable to step outside it, yet profoundly affected by its shape. This leads to the central question of this entire story. If the universe is space-time, does space-time itself have a history? Do the distances between all things evolve? Does the fabric of reality stretch or shrink? If the answer is yes, then the universe is not merely a background. It is an actor participating in the drama of existence. But the evidence needed to answer this question was not yet clear in Einstein's time. To uncover it, scientists would need to become detectives. They would gather faint traces of starlight, examine them like clues in a cold case, and read cosmic history, not through myth or philosophy, but through the precise fingerprints etched in the spectra of distant galaxies. Little did they know, the sky was already whispering the truth. All that remained was for someone to listen closely enough. This is where our investigation truly begins. What if the universe never wanted to stay still in the first place? What if Einstein's struggle to force his equations into a static cosmos was not a sign of mathematical elegance, but of human reluctance? After all, who truly wants to believe that everything's space-time distance might be shifting beneath our feet? And if the universe is moving, expanding, evolving, then what does that mean for our place inside it? This is where the story takes a surprising turn toward individuals who were not legends, yet not famous physicists, not Nobel laureates, not icons. They were outsiders thinkers on the edge of the scientific community. And sometimes, those are the people who see what no one else is willing to see. Take Alexander Friedmann. A Russian mathematician working far from the major centers of physics, he dared to ask a question almost no one asked seriously. What if Einstein's equations are right, and Einstein himself is wrong? What if space-time cannot remain static? What if the universe is forced by its own geometry to expand? Friedmann did the simplest thing possible. He trusted the mathematics more than the expectations. And the equations told a shocking story. A universe that stretches. A cosmic fabric that must grow. No gods, no myths, no metaphors. Just pure mathematical necessity. But here is the real question. Why did almost nobody believe him? Was it because he was Russian during a period when communication with Western scientists was limited? Was it because he challenged the giant of his era? Or was it because the idea of a universe that changes felt too radical, too alive, too much like returning to the myths scientists tried to escape? Whatever the reason, Friedmann's result was largely ignored. Some even dismissed it as a mathematical curiosity. Einstein himself first rejected Friedmann's work, only later admitting it was correct. But by then, Friedmann had already died young, never seeing his idea reshape the world. If Friedmann was the mathematician who cracked the door open, Georges Lemaître was the one who stepped through it. Another outsider this time, a Belgian priest with a talent for physics, Lemaître faced an even stranger challenge. How could a clergyman convince the scientific elite that the universe itself was expanding? Could he really propose that all galaxies were getting farther apart, not because they were flying through space, but because space itself was swelling? It sounds almost conspiratorial, doesn't it? A priest claiming the universe had a beginning and was growing ever since, while the scientific world clung to the comfort of eternity. Was he motivated by religious ideas? Was he trying to bring creation back into science? Critics whispered these things. Some still do. But Lemaître's genius lay not in his theology. It lay in his ability to connect equations with evidence. Unlike Friedmann, he looked closely at the strange observations already emerging from the sky. In America, a quiet, meticulous astronomer named Vesto Slipher had been pointing telescopes at fuzzy nebulae in the heavens. What he found seemed almost unbelievable. Their light was shifted toward red wavelengths. Why? What could make light stretch like that? Was it motion? Was it something happening to the light itself? Or most provocative of all, was it the universe playing tricks on us, masking its own expansion by altering the wavelengths of starlight? Slipher didn't know the answer, but he sensed a pattern. So did Lemaître. Yet at this stage, the mystery deepens. Slipher's data showed redshifts galaxies appearing to move away, but no one had measured their distances accurately enough to confirm anything. How could one detect expansion without knowing how far these galaxies actually were? Was the universe truly stretching, or were the galaxies simply drifting? Then came Edwin Hubble. Standing atop Mount Wilson, staring deeper into the cosmos than anyone before him. Using the powerful Hooker telescope, Hubble identified Cepheid variable stars in distant nebulae stars whose brightness rhythm allowed him to calculate distance with surprising accuracy. And once distance entered the equation, everything changed. Hubble discovered a relationship: the farther a galaxy was, the stronger its redshift appeared. The pattern was unmistakable. But what did it mean? Were galaxies genuinely speeding away from us, as if we were at the center of some cosmic explosion? Or was there another, subtler interpretation? Here, the conspiracy-like questions begin to creep in. Could it be that space itself was stretching, pulling galaxies apart, even if they never moved on their own? Could the redshift be a signature not of motion, but of expansion? And if so, what force? What hidden driver was capable of pushing the universe outward? Hubble proposed the simplest explanation: galaxies were flying apart. But simplicity is not always truth. What if Hubble, in his rush to explain the data, overlooked something deeper? What if he only saw the symptoms, not the cause? Because Lemaître, analyzing the same data, quietly reached a different conclusion. He believed the galaxies were not moving in space at all. Instead, the space between them was expanding. Was this idea too strange for the scientific world to accept, or too revolutionary, or perhaps too elegant in a way that made people uncomfortable? And yet, this interpretation would eventually become the foundation of modern cosmology. But not yet. At this moment in the story, we are left with questions layered on top of questions. If the universe is expanding, when did it begin? What set it in motion? Why is everything moving apart? And above all, what unseen force or principle dictates the behavior of space-time itself? The investigation is only halfway through. The clues are there, scattered across the sky, hidden in equations buried in forgotten papers. But it will take one more revelation a twist. No one expected to reshape our understanding of the universe forever. The real shock is still to come. What if everything we thought we knew about the expansion of the universe was only half the truth? What if Hubble's discovery, so monumental, so elegant, had actually concealed a deeper, stranger reality underneath? And what if the real story wasn't about galaxies fleeing through space at all, but about the fabric of reality reshaping itself beneath our feet? This is where Georges Lemaître stepped back into the light, with an idea that sounded almost unbelievable at the time. What if he asked the galaxies were not racing away from one another like shrapnel from an ancient explosion? What if they were actually standing still? Could the redshift, the great cosmic clue at the heart of the mystery, be caused not by motion, but by something even more dramatic? Space itself stretching. Imagine ink dots on a balloon. If you blow into the balloon, the dots do not move. The surface expands, increasing the distances between them. Could the universe be doing the same thing? And if so, what force is inflating this cosmic balloon? Is there a mysterious agent pushing space-time outward? Or is expansion simply woven into the geometry of reality? Something that must happen rather than something being caused. When Lemaître published this interpretation, few noticed. Even fewer believed it. Yet time has a way of exposing the truth. Eventually, the scientific community realized that a universe in expansion solved nearly every puzzle that Friedmann, Lemaître, and Hubble had uncovered. Suddenly, the pieces fit. Suddenly, the chaos had order. But accepting expansion led to another far more unsettling question. If the universe is expanding today, was it smaller yesterday? And if we go back far enough, does it all converge to a beginning, a point where everything was compressed into something unimaginably dense and hot? Could this be the ultimate origin event, the moment from which space and time themselves emerged? For decades, scientists debated this possibility. Some embraced it. Others resisted, fiercely uncomfortable with a universe that had a beginning. Was this scientific disagreement? Or was there an unspoken fear that such an idea echoed too closely, the old cosmogonies, too close to theological creation stories? Was science afraid of sounding like myth again? Yet evidence kept accumulating: the cosmic microwave background, the ratio of hydrogen to helium, the large-scale structure of galaxies. Bit by bit, the universe confessed. Expansion was real. A beginning was likely. Lemaître, once dismissed, was suddenly at the center of cosmology. Even Einstein eventually admitted that the static universe he preferred was an illusion of his own design. But just when physicists thought the investigation was complete, a twist arrived, one that shook the foundations of cosmology in a way even Einstein had never imagined. In 1998, two independent research teams studying distant supernovae made a discovery so shocking that some scientists initially believed they had miscalculated. The universe was not just expanding, it was expanding faster over time. Expansion wasn't slowing down as gravity should force it to. It was speeding up. How is that possible? What engine could accelerate the universe itself? Is there an invisible pressure embedded in the vacuum of space? Is space-time infused with a hidden form of energy, undetectable, unobservable, yet powerful enough to push galaxies apart faster and faster? This mysterious influence was given a name: dark energy. But naming something does not mean understanding it. Even today, no one knows what dark energy truly is. Is it a property of space-time? A quantum effect? A remnant of some primordial field that never decayed? Or is it something stranger? Evidence of hidden dimensions, parallel universes, or physics we have not yet imagined? And what does an accelerating universe mean for the future? Will galaxies drift so far apart that the night sky goes dark? Will atoms eventually be torn apart if expansion continues to accelerate? Could there be a final moment where space-time splits, ending the cosmos in a big rip? Or will expansion settle into a slow drift, leaving stars to burn out quietly in an ever-growing emptiness? These are not questions with easy answers. They sit at the boundary of what humanity knows and what remains hidden. But perhaps this is fitting. Remember Rilke's metaphor: we are bees of the invisible. We gather what little light we can. Fractions of photons, faint spectra, subtle distortions. And from these, we build our understanding of the universe. Maybe the universe does not reveal itself all at once. Maybe it opens slowly, layer by layer, each discovery leading not to certainty, but to more profound wonder. What if the greatest secret of the cosmos is not where it came from or where it is going, but the fact that we can understand any of it at all, as long as we keep asking questions, especially the uncomfortable ones? The hive of human curiosity will continue to expand just like the universe itself.